Hello everyone. In this lecture, we will study another feature of the graph. So we just shift a little bit from the digraph or the direct graph to the usual graph again. So here we will study the chromatic graph. So in this area, a very famous problem is the so-called four-color problem. We will not prove the theorem here. Neither we will do. Now we will do the five-color problem. If you are interested in this topic, you can look at the proof in your textbook. Because we only have two lectures left, so I want to save more time to new concept. And for the details, if you have interest, you can look at those by yourself. So the four-color problem can be stated as follows. Consider a map that is drawn on the plane or on the surface of a sphere in which the countries are connected regions. This is true for most of the countries, but in reality, there are some countries with two separated P's. Just like Russia, you have Königsberg, which is called flying field. Okay, and we want to color each region with one color so that neighboring regions are colored differently so that we can just tell which one is which. So the question is, will four colors always suffice? So the answer is yes, but up to today, I think all the proofs has some computer add feature. So compute add proofs. There are a lot of proofs, but all of them use computer. Okay, and so to study this problem, we introduce some notation. So first, let G be a graph. Notice that in this problem, in the coloring problem, it's not important the graph is simple or a general graph, because we only care about if a pair of vertices connected or not, no matter how many edges between them. Okay, also we don't consider the general graphs with loops, because in that case, the vertex with loops cannot be colored at all. So here a vertex coloring G is G is an assignment of a color to each of the vertices of G in such a way that adjacent vertices are assigned different colors. Okay, and if the colors are chosen from a set of k colors, then the vertex coloring is called k vertex coloring, or k coloring in short. And here noted that so even if we have the k coloring which use less than k colors, we can still call it k coloring. And then for the graph G, if G has a k color, yeah, so probably you have a lot of k colorings, but as soon as it has one, then G is said to be k colorable. And then the smallest k such that G is k colorable is called the chromatic number of G. And denoted by chi G. This is kind of standard notation used in the textbook, but probably in some research papers you might have different notation. The notation is not that important as a meaning or as a definition of the chromatic number. Just like there's old Chinese saying says, listen to what they say and watch what they do. So the most important thing is watch what they do, watch what the notation means. Okay. Okay, in the following, there's a very important concept called null graph. So here we give a formal definition. So a null graph is not an empty set, just a graph without any edge. With no edges. So if we have n vertices, then we can denote the null graph G equals V. This phi is not phi, it's empty set. Just a small remark. Okay, by n. Or if you have some confusion, you can change this to m, then it's nm. Okay, and it's apparent that chromatic number is an invariant associated with the graph. And then whenever you define an invariant, you want to know more. So for instance, okay, here, I would like to make a remark. So remark, chromatic number is kind of one-dimensional representation graphs. So here I use one-dimensional representation, not so rigorous, because if you learn a little bit linear algebra or abstract algebra, representation means something associated with linear maps, but here it's not linear. But the idea is the graph is very complicated, cannot be represented by numbers, just like you have some rocks or some field, there's oil, so how to test it? And usually what people do is give some gamma rays or X rays and to test it, so those rays are one-dimensional. So after you have some rays passing through the rocks or the field, you have some information. Okay, and then chromatic number is one kind of such one-dimensional representation, because you know the number is an integer, it's a non-negative integer. Okay. This gives some information of the complicated object graphs. This is a typical idea used in science. We want to simplify the model and forget about some not so important issues. For example, if we want to mention a student in class, we can use a student ID number instead of describing the person, who he is, or who is he, or who is her, and what are their hobbies, what do they do in holidays, kind of stuff. Those are important stuff associated with a person, but not so important in related to his or her academic grades. Okay, so whenever you have a real problem, you always want to simplify the model and drop sometimes even the majority of the object, but only leave the most important related stuff. Okay, so chromatic number, some kind of invariance describing the connectivity or the structure of the graph. Okay, after we define something, usually we want to ask what property does it have. So here we have an important inequality. So let G be a graph of order n greater than 1, then the chromatic number is between 1 and n. And moreover, the chromatic number is n if and only if G is a complete graph. Chromatic number is 1 if and only if G is a null graph. And the proof is easy. And so first, the inequality is easy. And we will just skip the proof and only focus on the moreover part. And for the moreover part, we first look at if G is a complete graph. So in any vertex coloring of Kn, no two vertices can be assigned the same color, because there's an edge between each pair of colors. So hence, the chromatic number is n. Okay, and the reverse, if chi n is n, and the vertices u and v o g are not adjacent, then we will have some contradiction as follows. Then we can color u and v by color 1, and so this is color 1. And color the remaining vertices v1, v2, all the way to vn minus 2 by colors 2, 3, n minus 1, 2, 3, blah blah, n minus 1. Okay, then the chromatic number of G at most n minus 1, because we already have an n minus 1 coloring of G. This is a contradiction. Okay, therefore, if the chromatic number is same as the order of the graph, then each pair of vertices have an edge incident with them. Okay, similarly for the graph with chromatic number 1, so if it's a null graph, then assign all vertices O and the same color, then chi n less than or equal to 1. But since n is greater than 1, so this is 1. And if G is not null, then there's an edge joining U and V. Then U and V cannot have the same color. In other words, chromatic number should be at least 2, which is a contradiction. Okay, another very interesting corollary follows immediately is that if H is a subgraph of G, then chromatic number of G is greater than chromatic number of H. This is because any coloring of G is also a vertex coloring of H. Okay, and the corollary of the corollary is that if G has a subgraph equal to or isomorphic to a complete graph Kp of order P, then chi chromatic number of G is at least P. So this is a combination of the previous theory and the lemma and the corollary. and use these we can determine the chromatic number of the following graph. So because we have triangle x, y, z, then chromatic number of G at least 3. Okay, on the other hand, we can use 3 colors to color the graph. Okay. And actually for K coloring, we can view it as a partition in the following sense. Let G be a graph that is K colored using the colors 1, 2, 3 all the way to K. So let VI denote the subset of vertices that are assigned the color I. Then V1, V2 all the way to VK is a partition of V called color partition for G. And the color partition is not arbitrary because the induced subgraphs GV1, GV2 all the way to GVK are null graphs. And this procedure can be reversed. In other words, conversely, if we can partition the vertices into K parts with each part inducing a null graph, then the chromatic number is at most K. And in other words, chromatic number of a graph is minimal for all K greater than integers, non-negative integers. For all vertices, OG can be partitioned into K sets, K subsets, or K sets with each inducing a null graph. And then if we have control of the null subgraph in a graph, then we have a control of the chromatic number from below. So in other words, we have the following corollary. So let G be a graph of order n and Q the largest order of an induced subgraph of G equal to a null graph NQ, then chromatic number is greater than or equal to the ceiling of n over Q. So the proof is easy. So let chromatic number be K and V1 to Vk color partition for G, then Vi, the cardinality of Vi is less than or equal to Q for each I, and hence the cardinality of V is n equals, because we have the partition, so the cardinality is a summation of cardinality of the subsets, and then we have less than or equal to summation of k q's, and this is kq, and therefore k is greater than or equal to n over q ceiling, because k is an integer. Okay, after we characterize graphs with chromatic numbers 1 and n, a natural question is how to characterize graphs G with chromatic number 2. So the theorem is let G be a graph with at least one edge, then chromatic number is 2 if and only if G is bipartity. So what is bipartity? G is called bipartity provided that the vertex set V may be partitioned into two subsets, X and Y, so that each edge of G has one vertex in X and one vertex in Y. So a pair XY with this property is called a bipartition of G. So in other words, graphically we can do the following. So on one side you have point vertex X, on the other side you have point Y, and all the edges are from X to Y. And in particular, so on the left-hand side, this is a null graph, null subgraph. And the same thing on the right-hand side. you have a null subgraph on the right hand side as well. Okay, and another remark is partition, bipartition might not be unique. For example, if you have 2 points on left, 2 points on the right, and you have connection like this, so you have bipartition. But on the other side, on the other hand, we can give another partition. You have 2 points, 1 point on the left, 3 points on the right. Go this way. This is another partition. Okay, another bipartition. So it's not unique. And also, it might not be so apparently. Easy example is A, B, C, D on left, U, V, W on right, and you may have multiple edges between A and U. But you cannot have loops because it contradicts with the definition. Okay, and this is very obvious, but then you have the following case. Okay, suppose you have this graph, and how can you tell this is bipartity or not? You need to work a little bit and find that. You can do the following bipartition: A, C, G, H, J, K on the left, and then B, D, E, F, I on the right, and then we need to do connection. A is connected to B, D, F, and C is connected to B, D, E. G is connected to B, E, I. H is connected to E, F, I. J is connected to B, F, I. K is connected to B, E, F. Oh, so sorry, here I made a mistake. G is connected to D, E, I. And J is connected to, J is also connected to D. and then K is connected to B, E, F. Okay, anyhow, the rearrange is complicated. So you have a balance. If you choose to do bipartition, then you have a messy edges. If you want to make the edges clean, then you miss the information of bipartition. Okay. So another way to do this, probably I guess, you can just circle them. Just A, C, G, H, J, K. So those are in the same group, and then remaining D, B, E, F, I in the other group. Okay, so they are separated. A blue dot, a blue vertex must be connected to a red one, and vice versa. Okay. Partity group. So definition: partity group graph G with bipartition XY is called complete, provided that each vertex in X is adjacent to each vertex in Y. And in our textbook, they use the notation KMN to denote the complete bipartition. So where M is a coordinate of X and N is a coordinate of Y. And of course, from the definition, we can derive easily that KMN is the same as KNM. They're isomorphic. And how to tell multigraph is bipartity or not? There's an easy criterion. So multigraph is bipartity if and only if each cycle has even length. So I will not prove this. Actually, we can fix a vertex X and define, or let's call this U, and define X to be Y to be tau alpha. Tau is a terminal. Oh, sorry. Here we don't have terminal. So Y. So Y. There's a path from U to Y with order length. And then X is remaining vertices. And how to use the condition? Because of the condition, Y is well defined. Otherwise, you may have a path from U to V, U to Y with order length, and another path from U to Y with even path, so even length. Then it's not well defined. But in our assumption, whenever you have a path from U to Y with order length. All the paths from U to Y have order length. Okay, now we turn back to the theorem. Recall that theorem claims if the chromatic number is 2, then G is a bipartition graph. So we first prove one direction. If G is a bipartity graph, then we can color the vertices on the left or the X by one color, and the vertices on the right, so this will be the Y part, by the other color. Then it's easy to see the chromatic number is 2. Recall that because here we use the assumption that G has at least one edge. Otherwise, we can only claim chromatic number is less than or equal to 2. And conversely, we can put vertices with one color on the left and with the other color on the right. Therefore, G is bipartity. Because of the definition, if we have two coloring, then we have a color partition of the graph with two parts, and each induced subgraph is a null graph. So this just what we need in the definition of bipartity. Okay, so this is done, and then immediate corollary is if G is not null, then chromatic number is 2 is the same as each cycle in G has even length. So this is a pure geometric characterization of the numerical quantity chromatic number. And then a natural question is, can we have some easy way to characterize graphs with chromatic number 3? Unfortunately, the answer is complicated. If you have interest, you can look at the reference given in your textbook or search on the Wikipedia. We will not repeat that. Okay, in reality, you might have a very large chromatic numbers, and how to give a color, although it's not optimal, it's not the number given by the chromatic number, but we still want some reasonable coloring. So this can be done by greedy algorithm for vertex coloring. So the greedy algorithm, how to understand the greedy? Greedy means it's actually a neutral word. There's no positive or negative meaning in our sense. Greedy means every time you only do the local maximum or local minimum. So that's called greedy. But in mathematics, of course, you can imagine what is global question, what is a global minimum. But in reality, in the daily life, we don't know what is global. The question is like, what is the meaning of a human being's life? it's quite out of control. We don't understand even now. What we understand is in every level, the local maximum or local minimum, local meaning. No matter how you construct your theory, how philosophically correct, we always do some kind of relatively local things. So this is a greedy algorithm. I just want to convince you that greedy is just a neutral word, meaning it's a local optimization problem. Okay, so let G be a graph in which the vertices have been listed in some order x1, x2, xn. And first step, assign the color 1 to vertex x. And secondly, for each I equals 2, 3, all the way to n, let P be the smallest color such that none of the vertices x1, xi minus 1, which are adjacent to xi, is colored P. And assign the color P to xi. And of course, without any information, we don't know what we have from the algorithm. Probably it stop in the intermediate step. We don't have coloring at all. So here we have a theorem which says that under some condition, the algorithm will return a reasonable coloring. So let G be a graph for which the maximum degree of a vertex is delta. Delta is a number. Then the greedy algorithm produces a delta plus 1 coloring of the vertices of G, and therefore chromatic number of G is less than or equal to delta plus 1. So proof is kind of easy. So there are at most delta vertices adjacent to xi, and hence at most delta of the vertices x1, xi minus 1 are adjacent to xi. Oh, no matter how large I is. So you can only have delta out of all the previous vertices adjacent to xi. Okay, then therefore, when we consider vertex xi in step 2 of the greedy algorithm, at least one of the colors 1 to delta plus 1 has not already been assigned to a vertex adjacent to xi. and hence the algorithm assigns the smallest of these to xi. Okay, we're done with theorem, and here we can make two remarks. The first remark is that the greedy algorithm depends on the order in which the vertices are listed. Okay, if you choose different orders, then the algorithm has different consuming time, and the result will be different. And secondly, actually this theorem can be strengthened a little bit, although the effort to the strong form is much more than the proof we give here. So Broca theorem, let G be a connected graph for which the maximum degree of a vertex is delta if G is neither a complete graph Kn nor an order cycle graph Cn. Cycle graph means you put all the points on a cycle and connect the adjacent ones. Then is less than or equal to delta. Okay, and you see, if we have all the cycle graph, then at least we need to have 3 colors. So this is strictly greater than the degree of the vertex of the vertices. And for a complete graph, we have the similar situation. So this kind of optimal. Next, we will study an important generalization of character numbers or organization of the chromatic numbers. So question, given a graph G and a set 1, 2, 3, 4 all the way to K of K colors, how many K colorings of G are there? And so therefore we define PGK to be the total number of K colorings of the vertices of a graph G. And the example, if K less than chromatic number, then PGK is 0. And also example, if we have a complete graph, then totally we have K times K minus 1 all the way to K minus M minus 1 for k greater than or equal to n. And also for the null graph, p is k to n's power. Because each vertex is independent, we have k choices. Okay, and a little bit more complicated is the case when a graph is a tree. So let T be a tree of order n. Then PTK is k times k minus 1 to n minus 1's power. So the proof, we just use the algorithm. But not the greedy algorithm, just growing algorithms for a tree. So you can use BFS or DFS or the general growing algorithm to grow a tree. Then the first vertex can be colored in k ways. Each of the remaining vertices has k minus 1 ways to be colored. Then totally we have PTK is k times k minus 1 to n minus 1's power. And interesting observation is that all the PTK we have is a polynomial when k is larger enough, when k is greater than or equal. Actually, this when k is greater than the chromatic number, PGK is a polynomial function. Okay. So we call such function the chromatic polynomial for the graph G. So we like polynomials in any sense. In computer science, whenever you have polynomial growth over time, then you can see URC. Okay, so the proof actually gives you an algorithm to compute it. So let x and y be two vertices of G that are adjacent. So let G1 be the graph obtained from G by removing the edge xy joining x and y, and let G2 be the graph obtained from G by identifying the vertices x and y. Then the k colorings of G1 can be partitioned into two parts, CK and DK. So where CK is defined to be all the k colorings of G1 in which X and Y are assigned the same color, and dk is set of all the k colorings of G1 in which X and Y are assigned different colors. And then of course PG1K is CK plus DK, and DK actually is the kinetic of DK is PGK, and the kinetic of CK is same as PG2K. Then PGK is PG1K minus PG2K. And noted that by this, actually we can prove by induction, because the vertices, the kinetic of the vertex set of G plus the kinetic of edge set of G is strictly greater than that of G1, and this is same for G2. Actually, this is 1 greater, and for this one we have 2 greater. Okay, then we can prove this by induction on the sum of kinetics of edge set and the vertex set. We can prove PGK is a polynomial when k is greater than or equal to 1. Oh, sorry, when k is much more greater than 1. And here we can also describe an algorithm for computing the chromatic polynomials of a graph. So let G be, we first introduce several notation. Let G be a graph and alpha an edge of G, and then G circle minus alpha defined to be the graph obtained just G1 as above from G by deleting alpha, and G product, circle product alpha. Those are subscripts. Those are graph obtained from G by contracting alpha or identify X and Y. So if you still have a little bit confusion, so I will explain like this. Suppose you have X and Y. Okay, and you have an edge between them, and outside you have, for example, alpha 1, alpha 2, blah blah, beta 1, beta 2. And then what is G cross alpha? Oh, this is alpha. This is, you put X and Y together. Okay, let me use a different color here. And the x, now you have x, which is also y. And you delete alpha. And the remaining you have alpha 1, alpha 2, blah, blah. And then you have beta 1, beta 2, blah, blah. So this is a so-called contracting or identify x and y. So contracting, and this is G. This is G cross alpha. Okay. And now let's describe the algorithm. Oh, okay. Before that, another notation is plus minus h means signed graph. Okay, let G be a graph. So the algorithm, just like you decompose G into final and final building blocks. Just like you are playing Lego, and finally you will just have a tiny piece. So put Kyle G to be the set consisting of plus G, one element, and while there exists a signed graph in G, Kyle G, that is not a null graph, do the following. First, choose a non-null signed graph epsilon h. Epsilon might be plus or minus in Kyle G, and an edge alpha or h. Secondly, remove epsilon h from Kyle G and put in two signed graphs. So one is epsilon h circle minus alpha, and the other one is negative epsilon h circle product alpha. Actually, this is just the algorithm we used in the proof of last theorem. And then finally put PGK to be summation of epsilon KP, so where the summation extends over all signed graphs epsilon h in Kyle G, and P is the order of h. And immediately we have two remarks. First, PGK, although the coefficients for each monomial is complicated, but we know that this is a polynomial of degree n, and the leading coefficient is always 1. And the second remark, if G has disconnected components G1, G2, Gm, then the chromatic polynomial is the product of the chromatic polynomials of each connected component. here is connected components. G2K all the way to PGMK. Okay. And we don't have time to talk about 5 colors. So this is for chromatic numbers. We will just stop here, and then we turn to the 5 color theorem. We are not going to prove that, but at least we can give you some basic tools. So let G be a planar graph. So planar graph means we can draw the graph on the plane without any intersection or edges in the intermediate. So then G divides the plane into a number of regions that are bounded by one or more of the edge curves, and exactly one of these regions extends to infinity. And one of the most important formula is Euler's formula. This also can be generalized to, or can be restated for the polygons. Probably you already learned in high school. Let G be a connected plane graph of order n with E edges and R regions into which G divides the plane. Then R is E minus n plus 2. There are many proofs, so here I give one of the proofs very concisely. So find a vertex X connecting to infinity. And for example here, X, and you have a lot of edges. Okay, and then deleting X and all edges incident with X. So assume here L edges incident with X. So here you have alpha 1, alpha 2, all the way to alpha L. Then we decrease the number of regions. By doing this, we decrease the number of regions by L minus 1. The number of edges by L, the number and the number of vertices by 1. And then by induction on L on M plus E plus R, we can derive the conclusion. Okay, so by this theorem, actually we can show that Kn is not planar when n is greater than or equal to 5. So just here I want to say that the reason I introduce the Euler's formula is that I want to show you that although the formula is quite abstract, but it can be useful in reality. For example, long time ago, we said that for K5, which is a star-shaped thing, there must be intersections in between. Okay, but for K3, K1, K2, K3, K4, they can be organized so that there's no intersection in between. So here we give a proof why this is true. So the theorem is only useful when we have some application for it. Okay. So more general, if G is a planar graph, there is a vertex whose degree is at most 5. So each region Fi 1 less than or equal to I less than or equal to R has at least 3 edges. Then 3R less than or equal to 2E. Because this is a graph, so you don't have a region bounded by 2 edges. And then E less than or equal to 3M minus 6. So this is by Euler's formula. This is because no region bounded by 2 edges. And on the other hand, we have D1 plus D2 plus all the way to Dn is 2E. So we have D1 plus D2 plus all the way to Dn less than or equal to 6m minus 12. Okay, then at least 1O di is less than or equal to 5. So we are done. Okay, I will stop here. Next time we will finish up with more invariants associated with the graphs.